Hello and welcome. In this video, we're going to talk about combinatorial proof. This is a really handy proof technique that also requires you to embrace a particular mindset when solving problems. Coming up with a combinatorial proof requires you to think like a mathematician rather than thinking like a calculator. But I'm getting ahead of myself, and we need to start at the beginning. So here's our first simple question. What is n choose k? I'll give you a few seconds to try to remember. Okay, so here's the answer you probably just came up with. N choose k is n factorial over k factorial times n minus k factorial. And you're right. This is the formula for n choose k. And whenever you'd see n choose k in the past, you would immediately swap in this expression, maybe cancel some terms, then use your calculator or computer to give you a numerical answer. However, this is not the answer that I'm looking for. And what's the reason why? It's because this is not the answer that helps you to think like a mathematician. So in other words, in this video, I am asking you to unlearn how you think about n choose k. See, what really matters is, what does n choose k mean? So when I ask, what is n choose k, what I really want to know is, what mathematical concept does n choose k represent? And so my question to you is, do you know the answer to that? What does n choose k really mean? And here's the answer. N choose k is the number of k sets of the set of n things. In other words, it is the number of subsets of size k of the set 1, 2, 3, all the way up to n. N choose k is an idea first and a formula second. And that's the mindset that you should adopt too. Now, I don't blame you for giving the n factorial over k factorial times n minus k factorial answer. That is correct, and that was the productive way to think about it in your previous experience. But what I'm asking you to do now is to make a mental shift. And the best way that I can help you with this change of perspective is to show you one of the most famous examples of this very phenomenon. Here's an image of a 1929 painting by René Magritte. Most of the canvas is taken up by a large brown pipe. Below the pipe are the words, in French, "This is not a pipe." Wait, that doesn't make sense, does it? Clearly it's a pipe. How can Magritte say that it's not a pipe? He created a picture of a pipe and it's clearly a pipe. Well, the point of the painting is to call attention to how a viewer creates meaning. In fact, this is not a pipe. It is a representation of a pipe. It's just paint on a canvas that looks like a pipe to you. It's not actually a real pipe. The title of this painting is The Treachery of Images. Magritte is pointing out that your eyes are lying to you. That's not a pipe at all. This is a self-referential painting that delivers a high-concept meta-message. Did I mention that Magritte is a surrealist? I probably should have mentioned that sooner. So here is my combinatorial homage to Magritte. I call it the treachery of formulas. Now, every time that you see n choose k from now on, you're going to think to yourself, this is not a formula. But I'm not done. I have 3 more treacherous formulas for you. I don't want to know the formulas or the actual numbers for these. I want to know what these symbols mean. Each one corresponds to a fundamental counting problem. Pause the video and see if you can give the interpretation for each of these formulas that you see. Okay, let's start at the top. 2 to the n seems so innocent and context-free. But in combinatorics, 2 to the n means something very particular. Someone is choosing a subset from the set of size n. And so whenever you see 2 to the n, remember, this is not a pipe. Someone is choosing a subset of the set of n things. Let's move on. N factorial. This is just the number of permutations of n things. Someone is lining those elements up, one after another, and that's it. All right, we're getting pretty good at this. How about this last symbol? Gosh, how do we even pronounce this one? This is the number of k-lists of the set of size n, a list that uses k of the available elements. The official name of this is the falling factorial, so n falling factorial k, but I like to call it n list k to match the n choose k name. Plus, it tells me exactly what the symbol means. Someone is making a list of size k using the elements of a set of size n. These are our 4 building blocks for counting problems. And remember, when you see these symbols, I want you to think first and use formulas later. And even when you start using those formulas, keep thinking. So now we are ready to try our first combinatorial proof. This slide shows a combinatorial identity. We have an expression on the left and an expression on the right. The two sides are equal, so they must be counting the same thing. But they are doing this counting in 2 different ways, and it's up to us to figure out how. The left-hand side jumps out at us right away. It's just 2 to the n, and this is just the number of subsets of the set of n things. So somebody is choosing a subset of the set of size n. Now this often happens in a combinatorial identity. One side is easy to understand and the other is more complicated. So let's look at the right-hand side. We have an n choose k, all right, so somebody is picking a k set, but we also have a summation indexed by k, and k goes from 0 to n. So we are considering many different possible values for k, and k is the size of our subset. So now I hope that you can see that the right-hand side is also counting all the possible subsets of n. And now we're ready to write a rigorous proof. So in fact, what we have for the right-hand side is a 2-step recipe. Step 1 is I'm going to pick a value for k. That's going to be the size of the subset I pick. And then step 2 is we are going to pick any subset of size k. So we're going to pick a k set from the set of n things. In other words, for the right-hand side, we first decide how big of a subset we want, and then we pick a subset of that size. And we do get every possible subset using this recipe. And the last thing I want to point out on this slide is that we're actually using the addition principle. See the summation sign? That's a bunch of pluses. That's a bunch of ors. We're taking k is equal to 0, or k is equal to 1, or k is equal to 2, and so on, all the way up to or k is equal to n, right? All those plus signs resolve to ors. And when we add up all those disjoint cases, we get all the possible subsets of n. So in summary, when we're looking at a combinatorial identity, we're looking for 2 recipes that count the same thing in 2 different ways. So we'll have to interpret the left-hand side and interpret the right-hand side, and then come up with an explanation for why these 2 recipes have actually constructed the same set of things. So here is another combinatorial identity, and I want you to explain this one to me. And so once again, remember, the left-hand side and the right-hand side correspond to 2 different ways to count the same set. Or equivalently, the left-hand side and the right-hand side correspond to 2 different ways to perform the same task. As in our last example, this left-hand side is easy. I think you can figure that out. And so your goal is to figure out why the right-hand side is also doing that same thing. And to help you out, I'm going to give you a pro tip. I want you to treat element n as special. In other words, I want you to focus on the element n and talk about what's happening to that element during your construction process. Good luck. Okay, I hope you were able to solve this one. Let's do it together. So the task at hand, according to the left-hand side, is to pick a k-set from the set of n things. So that must also be what's happening on the right-hand side. And then the guidance we got to demystifying that right-hand side is to treat the element n as special. If we're picking a k-set, and we're paying attention to the element n, there's really two things that can happen. Either that element n is in the case that we picked, or it's not. So I use the word or, and we have a plus sign. This is the addition principle. So those must be our two cases. All right, let's interpret the two sides of this equation. So now let's give the literal interpretation for each of the terms on the left-hand side. So this first one, n minus 1 choose k, we are choosing a k set from the set of n minus 1 things. And for the second one, n minus 1 choose k minus 1, we are choosing a k minus 1 set from n minus 1. And now I need to explain why this process actually creates all the possible k sets of the set of n things. Okay, this first term is just a k set that does not include element n. And so this means that the other term must correspond to the k sets that include the element n. Here I'm choosing a k minus 1 set and then add element n to get a k set that does include n. And now I've accounted for all possible k sets. And so the left-hand side is equal to the right-hand side. And we've proven our combinatorial identity. So now it's your turn. Here is another classic combinatorial identity. Now if I just showed you this formula, it might be a little perplexing, but I'm going to tell you the name of this formula. This is called the chairperson identity. And I'll just remind you what a chaired committee is. So a chaired committee is a collection of people, a committee that has a chairperson who's in charge of the committee. Right, so keep that definition in mind, and then look at this left-hand side and this right-hand side, and try to figure out why this is called the chairperson identity. What task are we accomplishing? And what are the two different ways that we can accomplish that task? All right, good luck and have fun.